And 7C.3 is a direct application of what we've been working through. It's called fair games. So it's a direct application of expected value. Now, the definition of a game that's fair is it's going to be fair if, what it says at the top, the expected gain, all right, so the expected value of the probability distribution is equal to the cost to play the game. So we have a simple game that costs $1 to play. It involves flipping a coin and guessing which side it lands on. If you guess correctly, you win $2. So what's going on with this distribution is we have two outcomes. You either lose, so you gain nothing, or you gain $2. And then the probability of each event occurring, we're saying it's a fair coin, so you have basically a 50% chance of guessing each way. Okay, determine if the game would be fair. Well, if we evaluate E of x here, okay, so the mean of this probability distribution, it would be 0 times 0.5 plus 2 times 0.5. Okay, this will simplify to 1. Now we're told a game is fair if the cost to play is equal to the expected gain. Now the cost to play is $1, and so what we can say is, yes, this is a fair game, as cost to play is equal to the expected gain. Okay, would this be good for a fundraiser? Okay, so let's say you're trying to raise money for your sports club or maybe do LARPing or whatever you're into, and you wanted to raise some money, all right? Basically what this tells you is on average, you're going to be giving out $1 and you're going to be earning $1. So this would not be a good fundraiser because every dollar that you receive, you would be giving back. So we can say no. Not a good fundraiser. For a game to be a good fundraiser, we would want the expected gain to be much less than the cost to play. Okay, let's move on to the second question then. We have a game costs $5 to play using a standard shuffled deck of cards. If you draw a face or an ace, you win $10. If you draw a 6 to 10 inclusive, you win $2. And if you draw a 2 to 5 inclusive, you win $1. Okay, so first let's draw the probability distribution for this. Because it says draw the probability distribution, that's part A. So for our events, the events are what can you win? Okay, so the lowest, and we should always put these in ascending order for the sake of determining the median. So the lowest you can win is $1, you can win $2, or you can win $10. They're the possible winnings. All right, so you'll always win something. All right, so even if you only win $1, you'll always win some money back. Okay, then let's do the probabilities of each of those events occurring. So in a standard deck of cards, right, we have 52 cards, and basically that means we have 4 suits, and there's 13 of each suit. Okay, so if we have we're told between a 2 and a 5, you win $1. So that's going to be a 2, a 3, a 4, or a 5. That's a probability of 4 out of 13. Okay, 4 out of 13 for one suit, but it's the same for all of the suits. So 4 out of 13, or you can think of it as 16 out of 52. Okay, you win $2 if you draw a 6 to a 10. So that's going to be a 6, 7, 8, 9, 10. This is a 5 out of 13. And then we can just do one take away those to determine this probability. Or you can think a face card means it has a face on it. That's a jack, queen, or king. Or an ace, that's 4 out of 13. So this is our probability distribution. Okay, determine if the game is fair. So here we're just going to calculate E of x. So the expected value of x is going to be 1 times 4 on 13, plus 2 times 5 on 13, plus 10 times 4 on 13. Now at this stage you can just put all of that into your calculator. I'm not sure where mine is, so I'll just, we've got 4 on 13, plus 10 on 13, plus 40 on 13, That takes us to 54 divided by 13. Alright, can someone nut that out quickly or try to find mine? Not too hard to find. So it should be just over 4.15. So 4.153, we'll round to three significant figures, 4.15. Okay, so that's our E of X. Now, the game is fair if the cost to play is equal to $5. We're told that at the start. Cost to play is $5. The game is fair if the expected gain is equal to the cost to play. So no, this is not a fair game. So we can just say E of X is not equal to cost to play. All right, now if you're running a fundraiser, this part B then says, would this be good for a fundraiser? If you're running a fundraiser, let's look at what's happening. Each time someone plays the game, they're giving you $5, and on average, you're giving back $4.15. That means on average, you're retaining 85 cents for every time someone plays the game. So this would be good for a fundraiser because you're going to be hanging on to money. You're going to be keeping money. All right? So as long as the expected gain for a player is less than the cost to play, you will be making money as the person running the fundraiser. So this is good. This is a direct application of our mathematics into the world of gambling.